Have you ever stopped to wonder, really wonder, what secrets are locked away in the rocks right beneath your feet? Or, how these absolutely colossal events happening over unimaginable timescales actually shape the Venezuela we see today? It's a question that really pulls you not just downwards, but way, way back in time, millions and millions of years. Welcome back to another deep dive. Today we're heading out on, well, quite an extraordinary journey deep into Venezuela's geological past. We're focusing specifically on one of its most foundational, yet maybe less talked about eras, the Paleozoic. And look, this isn't going to be just a dry history lesson. Think of it more as a dynamic, almost epic story. Continental collisions, vast seas flooding the land, the very building blocks of continents being laid down, setting the stage for the landscape you might be standing on right now. Our mission for this deep dive is, well, it's pretty ambitious. We're going to try and decode some complex geological sources to really get a grip on the fundamental transformation that happened in northern South America during this Paleozoic era.
We want to show you how these titanic movements of the Earth, things that happen so slowly we barely notice them on a human time scale, meticulously carved out the geography, the topography of modern Venezuela. It's a story of incredible forces and, frankly, a time frame that just boggles the mind.
It really does. And what's truly fascinating here is the sheer scale of time we're dealing with. The Paleozoic spanned nearly 300 million years. That's roughly from 541 million years ago right up to about 252 million years ago. I mean, just to put that in perspective, that duration is almost 6 times longer than the entire time the dinosaurs roamed the Earth. It's almost, well, it's nearly incomprehensible. But the events that unfolded during that immense period are absolutely critical for understanding the, let's say, the foundational geological architecture of Venezuela as we know it. The Paleozoic is, without a doubt, pivotal, not just for the planet's evolution overall, but very specifically for how Venezuelan territory got configured. It really shows us how the bedrock of modern Venezuela was forged, in this crucible of tectonic forces, sedimentary processes, building up history layer by immense layer.
Okay, let's try and unpack that a bit. You mentioned the sediments from this era. If we think about Paleozoic sedimentation in Venezuela, it sounds almost like it's caught in the middle.
Yeah.
Like a geological sandwich. Is that a fair way to think about it? Sandwiched between two huge mountain building events?
Yeah, that's actually a pretty good analogy, yes. It's
Yeah.
essentially sandwiched between two major orogenies. And for anyone listening, an orogeny is basically a period of intense deformation of the Earth's crust, the kind of thing that builds enormous mountain ranges. We're not talking small bumps. These are continental scale events.
Right, big stuff.
Exactly. So the first slice of bread, if you like, for our geological sandwich is the Caledonian orogeny. This happened way back at the very end of the Precambrian, maybe around 600 million years ago. And if you connect this to the bigger picture, the Caledonian orogeny was a fundamental turning point. It was such a massive event that, in many ways, it sort of reset the geological slate for what would come later in this region, northern South America. Imagine this huge continental crunch uplift. It prepared the ground, literally, for all those Paleozoic sediments we're going to talk about.
Kind of wiped the slate clean.
In a geological sense, yes. Pre-existing rocks were folded, faulted, metamorphosed, creating this new eroded surface ready for the next chapter of deposition, a major restructuring.
Okay. And then at the other end of the Paleozoic, the other slice of bread, we have the Hercynian orogeny. This is the one that really wraps things up, right? End of the Permian, beginning of the Triassic, maybe 250 million years ago, the grand finale.
That's precisely it. The Hercynian orogeny wasn't some minor postscript. It was incredibly active, incredibly widespread, and it fundamentally reshaped the entire area that would eventually become Venezuela. And the critical question then becomes, well, what are the implications of an event that's so active, so widespread?
Yeah, what does that actually mean on the ground, geologically speaking?
Well, an event of that scale implies massive tectonic compression, usually involving collisions between large continental masses or maybe smaller microcontinents. And that compression, it generates intense deformation over huge areas. It doesn't just lift up ancestral mountain ranges, it also causes widespread regional metamorphism, that cooking of rocks we talked about, and triggers the intrusion of enormous bodies of granite deep within the crust. Its sheer scale drastically reconfigured the paleogeography. You get significant uplift here, new sedimentary basins forming there. It essentially laid down the fundamental tectonic framework that continued to evolve right up to today, a genuine continental resculpting.
Okay, so we have these two massive continent-shaping events bookmarking the Paleozoic. But our sources also mention a third one, something more local happening about 475 million years ago, specifically on the South Andean flank.
Mm.
And that raises a question, doesn't it? How does a smaller event, kind of tucked away in one specific area, fit into this bigger story of continental transformation? Is it just a blip, or is it telling us something more subtle?
That's an excellent point, and it really highlights the complexity involved when you zoom in. While the Caledonian and Hercynian were definitely continental in scope, these more localized events, like the one 475 million years ago, they're often windows into the intricate stresses within that larger tectonic system. They aren't necessarily anomalies. They could be, say, the result of smaller ocean basins closing, or maybe little microcontinents bumping into the margin, or even just old zones of weakness in the crust getting reactivated. Even if it's less expensive, a local event like that could still cause significant regional uplift. And that in turn would profoundly affect where sediments were being deposited or eroded in that specific area. It could set the stage for later deposits or rework older ones. It's a reminder that tectonic activity isn't always, uniform across a whole plate. It can pulse locally with intense deformation. It's all part of this incredibly intricate dance of crustal blocks.
But it's not just one big shove, it's complex. And it's this complex interplay then between these different orogenies, the big ones, the smaller pulses, that define the boundaries and set the conditions for all the sedimentation and the changing geography, the paleogeography, that happened during the Paleozoic itself. It's like each orogeny turned a major page, dramatically resetting the stage for whatever came next.
Now, this is where I think it gets really fascinating. You have to try and picture the map of Venezuela looking completely different. Imagine vast areas submerged underwater. We're talking about a huge marine invasion, Paleozoic marine transgression that literally sculpted the primitive geography of what is now Venezuela. Picture it, a primordial sea covering huge swaths of land.
That's precisely what the geological evidence points to. In the roughly 250 million years after that initial Caledonian event we mentioned, a primitive arm of the sea, which was already there, started to steadily widen. And it advanced progressively northward. It eventually reached all the way up to the Perijá region. And this wasn't just a brief flood. This transgression continued quite significantly right into the Upper Paleozoic. By that time, huge stretches of what's now solid ground were completely under the sea. We're talking the Valera region, Trujillo, Táchira, all covered. And even a significant part of what's currently Lake Maracaibo was submerged. It paints a radically different picture of the ancient landscape, doesn't it?
Totally different. But was it all just flat underwater? Or were there like islands and things?
Good question. No, it wasn't uniform. There were really interesting exceptions. For instance, Merida, even way back then, seems to have emerged and formed quite a substantial island. You can picture it maybe as a rocky, high area surrounded by seas of varying depths. But then, in stark contrast, if you went over towards the Perijá region, the evidence suggests it was dominated by low-lying, swampy shallows, a very different kind of marine environment, perhaps more restricted.
And those differences must have mattered a lot for what kind of rocks formed.
Absolutely crucial. Merida, being an island, would have been eroding around its edges, shedding sediment into the surrounding waters. Sedimentation would concentrate around its flanks or in the deeper areas nearby. Meanwhile, those swampy shallows in Perijá, that environment would be perfect for accumulating fine muds and lots of organic matter. That could potentially lead to things like coal deposits or organic-rich shales forming later on. So yes, these environmental variations directly controlled the types of rocks that formed and, of course, the kinds of marine life that could flourish in each place.
It's amazing to think about that ancient geography. Now, pulling back even further, towards the end of the Precambrian and the start of the Paleozoic, the sources say northern South America was a positive area. What exactly does that mean, a positive area, and how does it connect to this big marine invasion?
Right. In geology, a positive area basically means a region that's topographically high compared to its surroundings. Critically, it means it's an area where erosion is the dominant process, not sedimentation. It's shedding material, not collecting it. So at the end of the Precambrian and the start of the Paleozoic, northern South America was essentially this. A vast elevated area. It had been undergoing intense, prolonged erosion for millions of years, wearing down older mountains and plateaus. Picture a huge ancient mountain range just slowly being worn flat by the elements.
Okay, so it was high ground being eroded.
Exactly. And that marine invasion we just discussed, this huge transgression, it happened precisely over these worn down zones. The sea gradually crept in over this landscape of, subdued relief. And it's at this point that a new geosyncline starts to form. Now, a geosyncline, Think of it as a long trough-like basin that's sinking, often linked to tectonic activity, and it accumulates immense thicknesses of sediments, sometimes volcanic rocks too. In this specific case, this new geosyncline began collecting the detritus, the eroded bits from those worn-down positive areas, those old highlands. And here's the key connection. The sheer weight and volume of these sediments accumulating in the sinking geosyncline, combined with increasing pressure and temperature as it got buried deeper, well, that was the process that eventually, over geological time, initiated the intense deformation and mountain building of the Hercynian orogeny we mentioned earlier.
Wow. So the erosion of the old mountains fed the basin that then became the new mountains.
In essence, yes. It's this fundamental cycle in plate tectonics. Erosion of old reliefs, deposition in a new basin, and that deposition eventually triggering the next round of mountain building. It's the Earth recycling its own crust, constantly reshaping itself.
So what does all this tell us then, this back and forth between land and sea, uplift and sinking? What's the big takeaway for understanding how continents and oceans work over Earth's history? Why should someone listening care about this ancient geological ballet?
Well, the profound takeaway is that the Earth's surface is anything but static. It's in constant flux. These marine transgressions and regressions, the sea advancing and retreating over continents, they're recurring themes throughout geological time. And they're driven primarily by two major forces. One is eustatic changes in global sea level itself, think melting ice sheets, or changes in the volume of the ocean basins due to things like seafloor spreading. The other driver is the tectonic movement of the continents themselves, uplift or subsidence.
So it's a mix of global sea level changes and local land movements.
Precisely. And the Paleozoic story of Venezuela is just this incredibly vivid example of how plate tectonics, global climate, and relentless erosion interact to continuously sculpt our planet over vast timescales. It teaches you that today's towering mountain might have been deep ocean floor millions of years ago, and what was once a vast plain might now be buried under kilometers of younger rock. Understanding these cycles gives you a much deeper perspective on just how dynamic our planet is. Continents assemble, they break apart, influencing life, climate, everything. It really makes you appreciate how temporary even our current geography is.
That's a great perspective.
Yeah.
Okay, to dive even deeper into Venezuela's geological makeup during this time, we need to get our heads around two key concepts. They sound a bit technical maybe, but they're apparently crucial for understanding where these Paleozoic rocks actually came from: autochthonous terrains and allochthonous terrains.
Yes, these are fundamental concepts, absolutely essential for piecing together how continents are built. So let's break it down. Autochthonous terrains. Think of these as the homegrown rocks. They formed in situ, meaning right there where we find them today, and they've basically kept their original position relative to the craton, that ancient stable core of the continent they belong to. They're the foundational bits, the ones that have sort of always been part of that continental block.
Okay, the native rocks.
Exactly. Now, allochthonous terrains. The name kind of gives it away. These are rock units or even entire chunks of crust that originated somewhere else, often geographically very distant. Through powerful tectonic processes, think plate collisions, things getting scraped off a subducting plate, a process called accretion, these foreign blocks got transported and then basically plastered onto or sutured onto an existing continental margin. They're the pieces that traveled from afar and joined the party later.
So like geological immigrants?
That's one way to think of it. And this distinction is vital because it reveals the complex assembly history of a continent. It shows that continents often aren't single, uniform blocks formed all at once. They're frequently geological collages built up over time.
Right, that makes sense. So applying this to Venezuela, where do we actually find these homegrown autochthonous terrains from the Paleozoic? And what story do they tell us about the really old origins of Venezuela's subsurface?
Okay, in Venezuela, the Paleozoic autochthonous terrains are mainly found deep underground in the subsurface of the Eastern Basin and also the Barinas-Apure Basin, specifically south of a major feature called the Apure Fault. And the dominant Paleozoic rocks you find in these autochthonous areas are these very distinctive sedimentary sequences known as red beds. Now, what's really fascinating about these red beds is the story they tell. There's strong evidence for continental rifting, the very beginning stages of continents pulling apart. Their presence points directly to the initial separation of two absolute behemoths. The supercontinents, Gondwana, which included what's now South America and Africa, and Laurentia, basically ancient North America and Greenland. You have to imagine the scale. The breakup of landmasses that enormous is a truly planet-altering event.
Wow. So these red beds are like the geological signature of that breakup.
Pretty much, yes. And we have further evidence in the Cambrian sequences that are remarkably well preserved deep down in structural depressions within those basins. Red beds themselves are typically continental sediments, things like sandstones, shales, conglomerates that form in arid or semi-arid conditions, often linked directly to rifting. Their distinctive reddish color comes from iron minerals oxidizing as the sediments were deposited, which points strongly to deposition on land under oxygen-rich conditions. The fact we find them buried deep now means they got covered by much younger stuff later on, but they're this invaluable record of those very first moments when these huge continents started to split. They're like ancient witnesses to a world transforming.
Okay, and then on the flip side, we have the allochthonous terrains,
Yes.
those traveling pieces that got added to Venezuela later. How do geologists tell them apart, and when did they actually arrive and get stitched onto the continent?
Right. The key criterion for distinguishing these allochthonous terrains is figuring out when they were tectonically accreted or sutured onto the northern edge of South America. And crucially, this wasn't one single event. It was a complex, staggered process that unfolded over immense periods of geological time. Our sources suggest we can broadly classify them based on when they arrived. There are distinct terrains that seem to have been sutured on during the lower Paleozoic. Then there are others that joined during the upper Paleozoic. And finally, there's a younger group that got incorporated much later, starting from the end of the Mesozoic onwards. This kind of temporal classification really underscores that mosaic nature of how continents grow. It's proof that continents aren't static. They evolve by adding new pieces over millions, even billions of years.
So if I'm getting this right, Venezuela isn't just one solid block. It's more like a geological quilt pieced together over time from different patches, some local, some from far away.
That's a very good way to put it. A geological quilt or mosaic.
And the last big piece of this allochthonous puzzle to get stitched onto northern South America, the one where we definitely find Paleozoic rocks, is basically what we now know as the Caribbean mountain system.
Precisely. That's a fantastic and very significant example of this accretion process. The Caribbean mountain system stretches over a huge area, doesn't it? From the Guajira Peninsula way out west, then dipping under the Gulf of Venezuela, popping up again in the Paraguana Peninsula, and then running eastwards along the whole coastal range, right out to the Paria Peninsula. It's a massive belt. And within this vast allochthonous terrain, yes, Paleozoic rocks have been confirmed, specifically dating from the Devonian through to the Permian periods.
Which makes you think, how on earth is such a huge chunk of land travel and then dock onto a continent?
It's incredible, isn't it? It's compelling proof of the power of plate tectonics. Massive crustal blocks can literally be rafted thousands of kilometers across oceans by the convection currents deep within the Earth's mantle. Eventually, they collide with and get accreted onto existing continents. And often, these allochthonous terrains have very different geological histories, different types of rocks, compared to the autochthonous basement they get stuck onto. That difference strongly reinforces their foreign origin and tells us about the complex assembly history.
So the big picture here is that Venezuela's geology isn't uniform at all. It's this incredibly complex mosaic of pieces, some original, some travelers, all assembled over hundreds of millions of years by these immense tectonic forces. Like a giant jigsaw puzzle, Earth has been slowly piecing together, each piece with its own backstory.
Exactly. A puzzle with a very, very long assembly time.
Okay, to get an even better handle on this Paleozoic era in Venezuela, let's break it down like geologists do, into the lower, middle, and upper Paleozoic. We can look at the key rock formations from each period and, maybe more importantly, what these rocks actually tell us about the ancient environments and the life that existed back then. They're like pages in an ancient stone book, right? Each formation, a different chapter.
Absolutely. Let's start that journey in the lower Paleozoic. This period gives us several really crucial formations. First up is the Miralus Formation. Lithologically, it's quite distinct. You see a lot of carbonaceous phyllites, dark ones, and also grayish-green phyllites. These are interlayered with what we call phylitic metashels, which can be massive or slightly schistose, meaning they show some alignment of minerals due to pressure. And there are occasional layers of quartzite and more grayish-green phyllites mixed in. But what really brings the Miralus Formation to life are the fossils. Geologists have found beautifully preserved trilobites in there, specifically a species called Parabolina argentina.
Trilobites, those iconic, almost alien-looking ancient sea creatures. What do they tell us?
Finding Parabolina argentina there, what does that imply about the sea conditions, the environment on that ancient platform? They're like tiny time capsules, aren't they?
They really are incredible fossils.
Mhm.
Trilobites, like Parabolina argentina, are classic marine arthropods from the Paleozoic. Finding them in the mirrorless formation strongly suggests a specific type of depositional environment, what we call a middle to deep marine platform. So think water that wasn't super shallow like a beach, but also not abyssal deep ocean. It was a marine setting with reasonable depth, maybe still within reach of sunlight at some levels, allowing enough oxygen and nutrients to support a decent community of organisms living on or in the seabed, the benthic community. And the rocks themselves back this up. The fine-grained phyllites and metashales suggest sediment settling out from relatively low-energy currents. That fits perfectly with the platform environment away from the high energy of the coastline or major river mouths. It paints a picture of relatively calm, productive ancient seas. Okay, calm seas with trilobites crawling around. Got it. What's next in the lower Paleozoic?
Next, we encounter the Cerrejón Formation. This one is characterized mainly by phyllites and metashales, similar in grain size, but as you go higher up in the formation, they transition into quartzites and even schists. What's particularly interesting here are the hornfells. Those are contact metamorphic rocks which become dominant in the upper levels. This tells us the Cerrejón Formation got cooked. It experienced significant metamorphism, most likely because hot igneous bodies, magma, intruded nearby, altering its original minerals and texture. It's a story of heat and pressure baked into the rock. Following that, we have the Cañote Formation. This shows a different mix. Micaceous quartzites, quartz-rich sandstones with mica flakes, arcosic metasandstones, sandstones with a lot of feldspar, cornubianites, another type of contact metamorphic rock, and some distinct lenses of metaconglomerates.
Hang on, metaconglomerates and those arcosic sandstones you mentioned. That sounds like evidence for stuff getting dumped quickly, maybe near mountains. High energy.
You're absolutely spot on, yes. Metaconglomerates were originally conglomerates, rocks full of large pebbles or cobbles that got metamorphosed later. Finding them, along with arcodic metasandstones, which, as you hinted, suggest rapid erosion of granite-like source rocks because feldspar breaks down relatively easily, is a very clear signal. It tells us the source area for these sediments was pretty close to where they were deposited. And conglomerates themselves require high energy to move those large clasts. We're talking powerful, fast rivers, maybe braided streams on an alluvial plain, energetic currents in shallow marine channels, or perhaps the front of an actively advancing delta. This kind of rock assemblage points strongly towards a landscape with significant actively eroding uplands nearby, likely ancient mountain ranges, shedding coarse debris into the basin. It gives you a picture of dynamic, energetic conditions, either riverine or nearshore marine.
Very different from the calm seas of the mirrorless formation, then.
Very different indeed. Now, still in the lower Paleozoic, we find the Cerro Azul Formation. This is described mainly as a greenish phylitic sequence. What's notable here, though, is the absence of fossils. No fossils have been reported from Cerro Azul.
So what does that mean? If you don't find fossils, how does that affect dating the rock or figuring out the environment? Does it just mean nothing lived there?
Well, the absence of fossils definitely complicates things. For dating, without diagnostic fossils, geologists have to rely on indirect methods. You might look at the rocks above and below it that can be dated, that's stratigraphic relationships, or you might try radiometric dating if there are suitable associated igneous or metamorphic minerals. Or you compare its rock type lithology to similar-looking, well-dated units elsewhere. As for the environment, a lack of fossils could mean conditions were harsh. Maybe the water was anoxic, lacked oxygen. Maybe the energy was so high it destroyed any remains. Or perhaps it was just a setting where macroscopic life wasn't abundant for other reasons, like unusual salinity. It presents a puzzle.
Okay, but some formations are rich in fossils from this time.
Oh yes, the Capera Formation, for instance, is much more giving. It has fossiliferous shales and some conglomeratic sandstones. And here we find a great diversity. Graptolites, trilobites, and brachiopods. This diversity is really significant. Graptolites, these tiny colonial animals, are incredibly useful index fossils for precisely dating rocks from the Ordovician and Silurian periods. And the trilobites and brachiopods, shelly animals, give us excellent clues about the conditions on the seabed. Then there's the El Horno Formation. This one features silicious shelly limestones along with shales and sandy shales, and again it contains fossil brachiopods. Those shelly limestones in particular typically point towards warm, relatively shallow marine waters where lots of organisms with calcareous shells could thrive, a lively ecosystem.
So lots of different environments represented already in the lower Paleozoic.
Absolutely. And finally, for the lower Paleozoic, we have the Tostos Association. Now, this is a complex mix. It includes slates, fellites, schists, even fine-grained gneisses, indicating higher levels of metamorphism, some massive siliceous rocks, and things called amphibolites. But the dominant rock types are phyllites and schists, showing significant regional metamorphism overall.
That lists slates, schists, gneisses, amphibolites. Sounds like these rocks went through a real ringer. Intense pressure, high temperatures. What kind of massive geological events could do that?
You're right, that assemblage screams intense conditions. Rocks like schists and gneisses, especially with amphibolites present, which often form from metamorphosed basalts or similar rocks, strongly indicate a history of major orogenic activity or perhaps subduction. We're likely looking at the deep roots of an ancient continental collision zone, or maybe a major fold and thrust belt where rocks got buried very deeply, or even an active subduction zone where oceanic crust and sediments were dragged down into the mantle and intensely altered. The strong alignment of minerals you see in schists and gneisses, schistosity, is direct evidence of intense directional stress during metamorphism.
But I think you mentioned earlier there's some debate about the age of Tostos.
Ah, yes. The age of the Tostos Association is actually a point of significant discussion, which is a fantastic illustration of how geological science works. It's constantly refining its interpretations. Originally, back in 1969, a geologist named Shagum suggested it was Upper Precambrian based on field observations. Later, Canelon and Garcia argued for a lower Paleozoic age, also based on field relationships. More recently, Belizia and Pimentel proposed a late Paleozoic age, mainly because it looks quite similar lithologically to another unit called the Mukuchachi Association. This disagreement really highlights the challenges in dating metamorphic rocks, especially without clear fossils. You rely heavily on field context, how the rocks relate to each other, and comparisons with other areas, but these interpretations can change as new data, like precise radiometric dates, become available. It's a great example of science being a process, not a set of final answers.
It shows how tricky piecing together this deep history can be.
It certainly does. And just to round off the lower Paleozoic, there's the Kachiri group, which itself is made up of several formations. You have the Los Guineos formation with things like breccias, angular fragments, silty shales, sandstones, and then dark limestones and marls near the top. The Caño Grande formation has sandstones below and then recrystallized shelly limestones and shales above. The Caña de Listic formation starts with shales and then has alternating silty sandstones and dolomitic limestones. And finally, the Campo Chico Formation has ferruginous gray wax, dirty sandstones, siltstones, and limestones, but this one is notably barren, no fossils found. Looking at that whole sequence tells you the environment was changing quite a bit. You go from possibly high energy settings producing breccias near faults or rivers to quieter conditions depositing shales and limestones. It suggests fluctuations in sea level or maybe shifts in where sediments were coming from. Those shelly limestones in Caño Grande definitely point to periods of clear water teeming with life.
Okay, that's a lot for the lower Paleozoic. What about the middle Paleozoic? You said earlier it was a shorter period, Devonian, Mississippian. Does the story get simpler or maybe more complicated?
Well, it gets more elusive, actually. The Middle Paleozoic record in Venezuela is notably patchy. As you said, it covers the Devonian and Mississippian periods. But the striking thing is its absence in several key areas. We don't find confirmed Middle Paleozoic rocks in the El Baol region, nor along that South Andean flank we discussed earlier. And specifically for the Devonian period, it hasn't been identified in all the wells drilled down into the Paleozoic in the central part of Lake Maracaibo. So there are significant gaps in the record for this time interval in those places.
Which brings us back to that earlier question. Does this gap mean nothing was deposited there then? Or did rocks form, but then get eroded away later, wiping that chapter clean? And why do we find Middle Paleozoic rocks in the Sierra de Perijá, if not elsewhere? What made Perijá special?
That's the classic geological puzzle, isn't it? Absence of evidence. It could be either non-deposition or subsequent erosion. Non-deposition means the area was simply above sea level or maybe underwater, but just not receiving any sediment for a long time. Maybe it was a structural high, an uplifted block. Subsequent erosion means deposits did form, but then the area got uplifted, exposed, and erosion stripped those layers away before the next sequence of rocks was laid down on top. Geologists look for clues in unconformities, those ancient erosion surfaces, to try and figure this out.
Right, the breaks in the sequence.
Exactly. Now, the fact that Middle Paleozoic rocks are found in the Sierra de Perijá is really telling. It strongly suggests that during that time, Perijá was likely a subsiding basin, a low area actively collecting sediments, while these other regions, El Baúl, South Andean Flank, Central Maracaibo, were either uplifted and eroding or perhaps just stable platforms where little to no sediment accumulated. It points to significant paleogeographical and tectonic differences across northern South America, even within this Suggle period. Some areas sinking, others rising. It wasn't a uniform playing field at all.
Okay, so a bit of a mysterious gap in some places, but present in Perijá. What happens as we move into the Upper Paleozoic then? The Carboniferous and Permian periods. Does the record become more widespread again?
Yes, it does. The Upper Paleozoic is generally much more extensively represented in Venezuela, which gives us a more complete picture as we approach the end of the era. For instance, if we look along the northern edge of the Guiana Craton, that ancient core of the continent, we find the Carrizales Formation. Its rocks are quite characteristic, mostly dark to greenish-black shales. These shales are dense, massive, pretty homogeneous, although they do have some silty intervals here and there. And importantly, there are also some localized interbeds of sandstones and even pebbly conglomerates within the shales.
Dark, homogeneous shales. That sounds like quiet water again, maybe deep.
It certainly suggests a low-energy environment, yes. Could be a relatively shallow marine setting, but one that was very stable, maybe a bit restricted, allowing mostly fine mud and clay to settle out. The dark color often comes from preserved organic matter, which might imply low oxygen conditions on the seafloor. Those occasional sandstone and conglomerate layers, though, they hint at interruptions. Maybe sediment washing in episodically from the nearby Guiana Craton during storms, or via intermittent river channels reaching the sea. So mostly quiet, but with occasional bursts of higher energy.
Okay, and what about further west, back towards the Andes?
Yes, along the South Andean flank, we also see significant Upper Paleozoic sequences. Several important formations there. First, there's the Mucuchachi Formation. This one is primarily composed of slates and something called conglomeratic metasandstones, plus metaconglomerates.
There are those conglomerates again. Then conglomeratic sandstones. Same interpretation as before. High energy, close to mountains. They seem to be shouting erosion, don't they?
Yeah, they absolutely are shouting erosion. Just like we discussed with the Cañueto Formation earlier, finding metaconglomerates and these coarse conglomeratic metasandstones in Mucuchachi is a clear, undeniable sign of a very high energy environment and close proximity to an actively eroding source area. The large clasts, often not very rounded, tell you they weren't transported very far. This kind of deposit often points to things like powerful braided rivers draining mountains, maybe large alluvial fans spreading out at the base of mountains, or possibly even glacial activity in uplifted areas. In the context of an orogeny, which we know was starting to ramp up towards the end of the Paleozoic, these coarse sediments are exactly what you'd expect. They're essentially the rubble being shed rapidly from rising mountain chains.
Makes sense. What else do we see in the Upper Paleozoic there?
Next up is the Sabaneta Formation. This shows an interesting progression. It starts with quartzo sandstones, quite clean quartz sands, which then gradually transition upwards into an intercalation, a mix of siltstones and sandstones. This kind of upward change or gradation is really informative.
How do geologists read that? Going from clean sandstone up into mixed siltstone and sandstone. What does that shift tell us about the environment changing over time?
That kind of upward transition, often called fining upwards if the overall grain size decreases, typically suggests a change in the depositional setting. It could mean the energy level of the system was decreasing, maybe the water was getting deeper, or the shoreline was moving further away, a transgression. Quartzo sandstones often form in high energy settings where weaker minerals get broken down or washed away. Think energetic beaches, maybe deserts, though less likely here, or shallow marine areas with strong currents. As you move upwards into finer siltstones mixed with sandstones, it could indicate a shift to a slightly deeper, quieter part of the marine shelf, or perhaps into a tidal flat environment, or maybe the outer parts of a delta building out into calmer water. Essentially, it's a sedimentary signal that the environment wasn't static. It was evolving, perhaps becoming less energetic, or moving further from the main source of coarse sand.
Okay, a dynamic system. And is there a final formation from this period?
Yes, rounding out the Upper Paleozoic on the South Andean flank, we have the Palmerito Formation. Lithologically, this is mainly a sequence of shales, marls, which are mixtures of clay and calcium carbonate, and limestones. And the key thing here is that they are all described as being highly fossiliferous.
Ah, fossils again. And you said earlier how important fossiliferous rocks are. What does the Palmerito's fossil richness specifically tell us about their value for dating and figuring out the ancient environment?
The Palmerito Formation, being so rich in fossils, is incredibly valuable. Geologically speaking, it's a gold mine. Firstly, for dating. If you find good index fossils, those species that lived for a relatively short time but were geographically widespread, you can date the rocks very precisely, often with better resolution than you can get from radiometric dating for certain time intervals. Secondly, and perhaps even more vividly, fossils are our most direct window into the ancient paleo environment. What kinds of organisms are present? How did they live? Bottom dwellers, swimmers, attached? How well are they preserved? All these details give us clues about water depth, salinity, temperature, oxygen levels, wave or current energy, nutrient availability. For example, finding corals or certain types of large shells often points to warm, clear, shallow seas. Finding certain microscopic fossils might indicate deeper water. In Repelmorito's case, with its mix of fossil-rich shales, marls, and limestones, it paints a picture of a productive marine platform environment. Conditions probably fluctuated a bit, sometimes allowing muds, shales to dominate, other times favoring carbonate production, limestones and marls, but overall supporting a diverse and thriving marine ecosystem. It really is through these tangible clues, these preserved remnants of ancient life, that geologists can painstakingly piece together what these long-lost landscapes and ecosystems actually looked like.
It's amazing what you can read from rocks and fossils. Okay, so we've journeyed through the lower, middle, and upper Paleozoic formations. Now we arrive at the big event you mentioned, right at the start, the grand finale, the Hercynian orogeny. This wasn't just the end of an era, was it? It was a massive transformation that basically reshaped Venezuela's geological foundations for everything that came after.
Indeed. It's the defining event that marks the transition from the Paleozoic into the Mesozoic era in Venezuela. You see its effects most clearly in the Permian period, especially in western Venezuela. This was the major mountain building event of the late Paleozoic here, and it triggered a whole suite of major geological processes.
What kind of processes are we talking about?
Well, several major things happened as a direct consequence of this orogeny. Firstly, we see the emplacement of large syntectonic granitic intrusions. Syntectonic means the granite magma pushed its way up into relatively shallow levels of the crust, while the tectonic deformation, the squeezing and folding, was actively happening. These granites are found particularly affecting the Venezuelan Andes, especially the central part, and also the Sierra de Perija. Their presence tells us that the crust was getting significantly thickened and heated during the collision, enough to cause widespread melting deep down, generating these large volumes of magma that then rose upwards.
So mountains forming and granite magma rising up at the same time.
Exactly. Secondly, there was significant regional metamorphism. This affected the older Paleozoic rocks across the central region quite broadly. Think of it as that large-scale high-pressure cooking we mentioned earlier. The intense pressures and temperatures associated with the continental collision and deep burial fundamentally altered the minerals and textures of pre-existing rocks. It's another sign of the intense conditions during mountain building. Thirdly, the Hercynian orogeny generated intense tectonic deformation. This means widespread faulting, complex folding of rock layers, and other related structural features. All of this was caused by the immense compressive forces squeezing the crust, and we see direct evidence of this compression in things like clayages developing in the rocks and the formation of expensive thrust faults, sometimes called planos de corrimiento.
Okay, you mentioned cleavages and thrust faults before. What exactly do those structures, those scars in the rock, tell us about the direction and the intensity of the forces involved? They sound like geological fingerprints of the collision.
They really are like fingerprints, yes. Cleavage, or rock cleavage, refers to those closely spaced parallel surfaces or planes of weakness that develop in fine-grained rocks when they're squeezed under immense pressure. Crucially, cleavage planes typically form perpendicular to the direction of the main compressive stress. Thrust faults are basically low-angle reverse faults, where one huge block of rock is pushed up and over another block. This directly accommodates horizontal shortening of the crust. The crust is literally getting squeezed shorter horizontally.
So the way they're oriented tells you which way the squeeze was coming from.
Precisely. If you measure the orientation of these cleavages and thrust faults in the field, you can work out the direction of the principal stress that caused them. For instance, if the cleavages are mostly vertical and trending north-south, it suggests the main compression was east-west. If the thrust faults consistently show movement from east to west, that also points to east-west compression. Furthermore, the intensity and density of these structures give you a sense of the magnitude of the deformation. Are the cleavages pervasive? Are the thrust faults large-scale, moving rocks for many kilometers? More intense features generally mean stronger compressive forces and greater amounts of crustal shortening. These structures are the tangible proof of the colossal pressures the crust endured.
Incredible. And apart from squeezing and cooking the rocks, did the Hercynian orogeny change the actual map, the geography?
Oh, absolutely. It caused major paleogeographical changes. We see evidence for a significant uplift along the northern margin of the Guyana Craton. That ancient stable block got pushed upwards. There was also a widespread marine regression. The sea retreated northward from western Venezuela. This is clear evidence of broad regional uplift of the land. And perhaps most importantly for the modern landscape, this period marks the initial significant topographical uplift of the ancestral Andean mountain range. Geologists sometimes call this the Merida Arch, and it seems to have had a northwest-southeast trend at that time.
So the Andes you see today, their story really begins back here in the Permian.
Their deep structural roots, yes. While the modern Andes owe a lot to much later Cenozoic uplift and deformation, the fundamental blueprint, the initial uplift, and the structural grain was largely established during this late Paleozoic Hercynian event. These weren't just minor local adjustments, this was a fundamental reconfiguration of a whole continental margin. It set the stage, laid the foundations for the geography that would continue to evolve into the Venezuela we see today. It's powerful proof that the deep geological past directly shapes our present landscape.
Wow. We have covered an immense amount of ground, or rather an immense amount of time. We've journeyed through nearly 300 million years of Venezuelan geological history in this deep dive. From that early Caledonian orogeny setting the stage, through the vast Paleozoic seas that flooded the land, piecing together the story of homegrown autochthonous rocks and traveling allochthonous terrains, looking at the specific clues and formations from the lower, middle, and upper Paleozoic, and finally arriving at that transformative Hercynian orogeny, the event that uplifted ancestral mountains and truly closed out the era. The Paleozoic was clearly a time of absolutely monumental change for Venezuela.
It truly was. And we really hope this deep dive has managed to convey not just, lists of formations and events, but the compelling, intricate story of how Venezuela was actually forged, layer by layer, collision by collision, over a time span that just dwarfs human history. And even though millions upon millions of years separate us from these events, it's the remnants, the rocks themselves, the folds and faults, the tiny fossil shells that allow geologists to read this amazing history. Geology really is the Earth's memory.
So, to leave our listeners with something to think about, maybe a provocative thought. When you look at the Venezuelan landscape today, the shape of the mountains, the distribution of the plains, maybe even the resources beneath the ground, what details might you now recognize or wonder about as potential echoes of this incredibly distant Paleozoic era? How does this deep geology, something that happened hundreds of millions of years ago, continue to be a living, tangible force, shaping not just the land, but perhaps even the life and history unfolding upon it today? Thank you so much for joining us on this, incredibly deep dive into Venezuela's Paleozoic past. We hope it sparked your curiosity to keep exploring the secrets the Earth holds beneath our feet. Until next time.